Cult of the Lamb is a new indie roguelike with over 1 million players in its first week. And in this video, we're going to be looking at a minigame within it called Knucklebones. Knucklebones is a really interesting game. It's super simple. We'll go through the rules in a minute. It feels a little bit like backgammon or something like that. You roll dice, you make decisions, you're trying to outscore your opponent. And we spent the last week or so on Twitch implementing a solver for it. The goal of the solver isn't really just to solve Knucklebones. After all, it's a mini game inside of a larger game. The AI isn't that strong in the first place, so it's not that difficult to beat. The goal is really to understand games like this, and in this video we're going to go through sort of the thought process behind how we implemented the solver and some of the insights we got out of it. If you're just here for the insights, that's fine. There are timestamps in the video. You can skip ahead to those. The GitHub repo is also available. There's a link in the description. You can clone it and run solves yourself, or you can play against the solver and see how you do. All right, let's get into it. So here is Cult of the Lamb, and here's the Knucklebones dice game minigame. So we can pick an opponent, and doesn't really matter. We can make a bet because I may as well get money. And so I could jump into the how to play here to show you the rules, but I think it's honestly easier to just see an actual example game. Makes more sense. So the first thing that happens is the player, one player gets to go first. In this case, Flinky. It's 50-50. And Flinky rolled a 1. And the goal of the game is to have the highest total number of dice at the end of the game. Game will end when one player's grid is entirely full, and we'll add up the score totals. But there are two kind of modifiers to the score totals, and we're about to see the first one here. So if I just put my 1 that I rolled over in this column, it would just get put here, and we would both have 1 point. But if I put dice of the same value opposite my opponent's dice, or if Flinky does that to me, then it eliminates the opponent's die or dice. So in this case, I'm going to put it here, and we're going to see that Flinky's 1 is eliminated, and he was annoyed by that. Flinky rolls a 3, places it. We roll a 5, we will place it as well. He rolls a 5 and eliminates our 5. Okay, Flinky is beating us at the moment. We roll a 4. 2. Okay, so here's the second modifier. If we double our dice, so if we have dice of the same value in the same column, it doubles those dice. So here we have 1 plus 1 is 2, doubled is 4. Let's eliminate his 6. And the same thing is true of triples. So he eliminates my 6, okay. Let's eliminate his 5. So if you have triple dice in a column, it triples the value of that column for you, and there we go. So this is 3 times 3 is 9. I think we're, and we would like to be able to eliminate his 2 3s, but we can't because we already filled up that column. So let's place it here so that we leave ourselves opportunities to eliminate his 6 for longer. We're getting pretty well trounced though, I think, although we might be able to finish first. Okay, that was a bad roll for him and a good roll for us. We might end up winning this after all. That was a good roll for him, and that was a good roll for us. Okay, I think we win that. Yeah, we win that. Okay, 68 to 46. Why 68 to 46? Just to go through it. So 9 plus 36 is 45, plus 23 is 68. And likewise, we could do the arithmetic here. 6 and 6 is 12, times 2 is 24, plus 1 is 25, and so on. And so we compare our scores, and we win. And that's Knucklebones. And so I set out to create a solver for Knucklebones. And what I mean by that is a bit of software that I could pass a position into. So I could say, hey, player 1's board is this. It's got a 2, 5, and a 6 in the first row, 1 blank 2 in the second, and so on. Player 2's board is this, 6, 6, 1, 1, 4, 2, etc. And player 1 has just rolled a 6. what should player one do? What is the best possible position for this 6 to be placed to maximize player one's chance of winning the game, assuming that player two plays perfectly also. So at each level, it's like, what are the optimal moves? And we want to find out, what's the best move for player one, and how does player two respond? And so before even writing any code, the thing I had in my head was the game tree. And so all strategic games have game trees, and it's kind of a simple idea. A lot of people have heard of it before. The idea is that, you're faced with, you're at some point, we call it the root of the tree. You've got this position, you've just rolled a 6. You have two legal moves, right? You can put a die here in the middle, or you can put a die here in the bottom right-hand corner. Those are represented by 1, 2. So this is the 0th row, the first row, the second row, 0th column, first column, second column. And so 1, 1 is this middle guy here. 2, 2 is the bottom right-hand corner. So those are the two legal moves. And from there, what can happen? Well, player 2 can roll a 1, a 2, a 3, a 4, a 5, or a 6. And based on those rolls, then player 2 has, multiple moves that they can play. Actually, yes, because we rolled a 6, and in this case we placed it at 1, 1. That eliminated this 6 here. So we player 1 played in the middle. Player 2 got their 6 eliminated, and so now player 2, when they roll a 6, now has 2 moves. They can either replace their 6 in 0, 1, or they can play 0, 2, the blank that was already here. And it continues, right? So now there are 6 possible rolls for player 1, and so on and so forth. And so this structure, this tree, is kind of the canonical thing that you want to be thinking about when you go about trying to solve a game, or even just think about a game. If you're thinking about chess, chess engines or even chess players, they think multiple moves ahead, and there are these kind of branching lines, and it's the same idea. The branching lines are the tree, and the chess engine is just looking at all of those possible outcomes in a smart way and trying to figure out the best one. The trouble with this game and many games is that the tree is huge. So this is an end game situation in Knucklebones, right? There are 2 blanks here, 1 blank here. The game is almost over, it seems like, except, you can see here on the side of my screen, the tree is still enormous. It still goes, 2,000 some odd lines deep. And that's an end game situation. If you're starting from a blank board, you're going to have something like 9 factorial times 8 factorial times 6 to the 17th power or something, possible combinations, possible branches of the tree or nodes in the tree. And that's not even including elimination. So once you have elimination, you have cases like the one that we saw a moment ago, where player 2, by the time it's player 2's turn, they have more than just the 1 move because this 6 got eliminated. So that makes for a very big game tree, which means we can't just construct the whole thing. That's a huge number. That number that I just said, it's more than 100 trillion. It will not fit in my computer or any computer's memory. So we have to do something smarter than just build the whole tree. Given that we can't just solve the whole tree, we need some way to work with smaller pieces of it. We need some way to estimate or approximate the solution and try to get close enough that we're essentially solving the game. And to do that, we're going to do something similar to what chess engines do, where we're going to look only some number of moves ahead, only 6 moves ahead, 4 moves ahead, something like that. And we're going to evaluate the position there. We're going to have some heuristic that says, well, okay, at a position like this, who's winning? Is there some way that I can tell without actually playing out this whole 2,000 move tree? And so how do we go about coming up with a heuristic like that? We want a number. We want to say that player 1 is plus 20 to be winning, where 20 means that they're doing better than if they were plus 10 or plus 5. 0 would be they're expected to draw, and negative numbers would be they're expected to lose. And so one way we can think about this is if we didn't have doubling and tripling of scores, and if we didn't have eliminations, that'd be a very boring game. It would be entirely based on chance, essentially. You would just be trying to fill up your grid with die rolls, and then you're going to add them up at the end of the day. It doesn't matter where you put your dice, because you're just going to add them up at the end of the day. So far less interesting game, much easier to come up with a heuristic. And one heuristic that we might sort of hit upon if we do that is to look at the differences between the two players' scores. Because that's kind of, at the end of the day, the thing you care about. If the difference between the scores is equal, then it's a draw. If it's positive, then we'll say we're taking player 1 minus player 2, so then player 1 would be winning. If it's negative, then player 2 would be winning. And that kind of seems to do a nice job of summing up what how you would evaluate such a position. One thing it misses, though, is it doesn't take into account that one player is likely to be left with empty squares, right? So it's player 1's turn here, but player 1 isn't, in all likelihood, isn't going, well, without elimination, they're not going to be able to populate both of these squares. They're going to move somewhere, and then player 2 is going to end the game, leaving player 1 with a blank. And that's not really factored in if we just take the differences, and that's even more extreme. You can come up with more extreme cases than that. And so, how could we sort of modify this heuristic? Well, we could say, let's just pretend that the blanks get populated by an average die roll until one player fills up their grid. So an average die roll is the average of 1, 2, 3, 4, 5, and 6. That's 3.5. And so let's pretend that he's going to have a 3.5 here, and player 1 is going to have a 3.5 here, or here, it doesn't matter. And then the game's going to be over because this one's filled up, and so player 1 doesn't get their last 3.5. And now we've kind of taken into account the power of position, you might say. So the power of you being the one who gets to end up playing the final move. In this particular case, it's not going to matter because we're going to have 3.5 here, 3.5 here. We're going to take the difference, and they're going to cancel each other out. But if we had, if the position was something like this instead, well, now player 1's going to probably want more. Player 1's going to go. Player 2's going to go, player 1's going to go, and the game's going to be over. And there are going to be 3 blanks left on player 2's board, which that's quite a few points that player 2 never gets. So that's our idea for a heuristic. Let's think about how that plays out when we incorporate doubling and tripling into the game. Well, all you have to do is make sure that when you take those totals, you take into account doubling and tripling. In this case, there's a double 6. We just when we take that difference, we need to make sure that in fact we've taken into account the fact that the 6s will be doubled, and we seem to have dealt with our heuristic seems to take into account doubling and tripling if we do that. One way it's not taking into account doubling and tripling is that we're assuming an average die will populate each of the blank spaces, But in fact, the player is going to be able to do better than that usually, because they get to choose where their dice go. And since they're trying to maximize their score, they're going to tend to choose to double the dice where they can, or triple them where they can, which means you're going to do better than your average of a 3.5 die roll. So we should kind of keep in the back of our minds that maybe we're understating the value of getting to play a die on a blank space. Now let's think about what happens when we add eliminations, the elimination rule back in. Does that affect our heuristic? Well, our heuristic is not taking eliminations into account. It's assuming that eliminations don't ever happen again, and so the players just, one player goes, the other player goes, they go back and forth until the end of the game. We saw how in this example, that's certainly not true. For instance, if we play the 6 here, it eliminates player 2's 6, and now the game tree evolves differently, right? Player 1 might fill up their board before player 2 does. Notice that means that we're overstating the value of position being the one who finishes the game first, or who's likely to finish the game first. We're kind of pretending, again, if we took a case like this, where player 2 is going to, looks like they're way behind, they're out of position, player 1 is in position, it looks like the game's going to be over after 1, 2, 3 more moves. Once the player 1 gets to go 2 times, it looks like the game will be over. That's if there's no elimination. If there is elimination, well, then it gets more complicated. Position isn't permanent in this game. It goes back and forth. And by assuming in our heuristic that it is permanent, we're overstating the value of position. So we're overstating the value of those 3.5s, essentially, that we assumed were going to be put in there. But if you remember, we're understating the value of the 3.5s from the perspective of doubling and tripling our dice. So there are kind of these two effects that are potentially canceling each other out. We don't know what their magnitudes are. Maybe one of them is way more important than the other one, but they go in opposite directions, and intuitively, it's certainly not obvious to me. It certainly wasn't obvious to me before I did this, which one would kind of beat the other one out. And so I decided that this heuristic of take the difference between the boards, assume that no more eliminations were going to happen, and use an average die, a value of 3.5 for all of the blanks that are going to get filled in. I decided that heuristic seemed like a good one, and that's what I ended up implementing. And you can actually see those showing up in the tree here. So if our player 1 places the 6 at 1, 1, and then player 2 rolls a 1 and places it at 0, 1, and then player 1 rolls a 1 and places it at the last spot at their 2, 2, the heuristic is being evaluated to -3. And I won't do the math here, but that is indeed, if my blanks were set up correctly, in this board, that is indeed the heuristic I just described would get you to -3 if the board's filled up that way. Before we jump into the insights, I wanted to point out one more thing about this game. This game is symmetric around the different rows. What I mean by that is it doesn't matter if you're going to play a move in a certain column. It doesn't matter where in that column you play it. And that's what I've done in the solver. So you can see in this position, we have the players placed a 4, the opponents placed a 1, players rolled a 1. And so there are 8 possible places for him to place that 1. Now it might be kind of obvious that any of the 3 in the first column is best, but the tree that the solver will calculate only has 3 moves in it. It only has 0, 0. That's going to correspond to any of the 3 moves. They're all the same. 0, 2. That's going to correspond to any of these 3 moves in the second column. 0, 1, 2, so the second column, and 1, 1, which is going to correspond to either of these two moves. And those are the only moves that matter, that are different than the other moves in their columns, and so those are the only ones that we're going to consider. Okay, so before we look at the solver results and try to get some insights from that, let's make a few predictions. It's always useful to make predictions when you do something like this because it helps you kind of A, work out whether the solver is doing what you expect, make sure there are no bugs, but B, figure out what you think is going to happen so that if you're surprised, you know to dig into it and try to learn something from it. Okay, so let's take a look at some solves. So starting off here in the starting position, we would certainly expect that any of the opening moves is a reasonable opening move, and indeed the best moves are any of the columns. Once again, this won't show other moves because it's only going to show one move per column, since it doesn't matter where you go within a column. And we kind of see, we rolled a 1, we're saying as player 1, and so the evaluation has immediately swung negative. It's swung to player 2 because we've rolled under average, right? 3.5 would be average, and so we've kind of rolled 2.5 points worse than that. Our heuristic, on the other hand, is giving us 3.5 points for position, and then there's some depth to the solve, and so we're ending up saying it's kind of -1 for player 2. It's in player 2's favor by -1 when player 1 rolls a 1 at the beginning of the game. So this makes sense. If we take a look at the next situation that I mentioned in the predictions, where player 2 has moved and it's player 1's turn and we've rolled a 4, where should we put it? We actually see that solver is indifferent between the 3 columns, which surprised me. I had an intuition, although I don't think I could have explained why, that we would want to play in one of the fresh columns. And so I thought this might be an interesting case to try to solve at a slightly higher depth, which I did. So in general, I used depth 4, seemed to be pretty good. But depth 6, we want to use even depths. And depth 6 is not prohibitively slow. And so I tried that as well for this solve. And I get that solver actually has a preference for the 0th column, for putting the 4 across from the 1. And this surprises me a little bit, and I haven't dug too deeply into why this would be. It's worth noting that the difference in evaluation is very small, so it likely doesn't make a huge amount of difference. But this situation comes up a lot in the game, and so it makes sense to take advantage of it. And I did test it with a different value on player 2's board. So rather than player 2 having rolled a 1, looking at the case where player 2 had rolled a 6, and the same story is true. On depth 4, all of the moves are equal, but on depth 6, the best move is to play across from the 6. And so I'm interested in this. I might drill down a little further and try to figure out what's going on here. But this is a really simple takeaway from this solve that I'm pretty sure is robust. I tried a bunch of other cases, and it just seems like in general you want to play on, if you're going second, you tend to want to play your roll across from your opponent's roll. I'd be interested if anybody has ideas as to why this might be true strategically. I would love to read about them in the comments. Great, so then we looked at doubling and tripling, which are obviously better than not doubling or tripling. And we looked at elimination, which is obviously better than not eliminating and not doubling, not tripling. But we had this case where we have 2 4s in play already. We roll a 4 so we can triple, but opponent also has a 4, and so we can eliminate as well. What should we do? Should we triple? Should we eliminate? And computer here shows us the answer in this case is to go 0-1. That's this one. So that corresponds to eliminating. Computer once says, hey, it's more valuable to eliminate your opponent's 4 than to try to triple it up. And we can think about why that might be. So what is this 4 worth as a triple? Well, it's worth 12 times 3 is 36, minus the fact that you're going to have 16 already here. So that's 20. When you eliminate, you're getting 4 points. You're subtracting 4 points from your opponent. So that's like 8 points already. We're also up a lot of tempi. A lot of tempi. And so we're winning hugely already. And so computer, in this case, is saying, look, 8 points plus we're getting 2 more tempi, which is worth something like 7 points. So we're kind of at 15 points here versus 20 points. But also we want to get closer to the end of the game, and it doesn't matter if you win by by 40 or by 30. We want to finish the game, and we don't want to put ourselves in a position where we have triple 4s that can be eliminated if our opponent rolls a 4. And so I think this is a case where the fact that we are winning by so much, and this is a theme we'll see come up again, we're winning by a lot. We want to mitigate our downside risk. We want to get closer to the end of the game. Elimination becomes more valuable than tripling, and in particular, tripling becomes riskier. I was interested to look at it, what if these were 6s instead of 4s? What if they were 5s instead of 4s? So let's look at it with 6s. With 6s, opponent has 1 6, we have 2 6s, and here when we roll a 6, computer is like, yeah, no, it's actually better to triple. Tripling is so good here. We're talking about 18 times 3 points. That's a lot of points. That's better than eliminating. And so there's kind of a cutoff here, and it's somewhere between a 4 and a 6. So I ran this again with a 5, and with a 5, computer still says triple. So in this exact situation, the computer wants us to triple 5s and 6s and eliminate 4s and presumably below. Now, if we looked at this position, but we didn't have these 1s here, so the position was closer, and we weren't as close to the end of the game, I suspect then that tripling becomes more valuable, and so maybe now tripling 4s is good. But the main takeaway I have here is that it takes a really strong double or triple to outweigh the benefit of eliminating even one of your opponent's moves. And so I think the way to interpret this is you should be looking at a hierarchy of options when you play a game of Knucklebones. You should say, look, I just rolled something. Can I eliminate my opponent's dice? If so, I should probably just do that, unless there's a really strong reason not to. If not, can I triple? If not, can I double? If not, can I play it in the same column as one of my opponent's dice? And if you follow that basic algorithm, eliminate, triple, double, same column, and you use some common sense, you're going to do really quite well. And the way that I went about sort of getting a sense for what the solver does here and finding some of these interesting situations is I just played against the solver. And I looked for situations where the solver doesn't follow that rubric. And it's unusual. So we can actually do that here. So if we run this command, this is the solver's location. You can get this off of my GitHub, and the command is play. So solver rolls a 6 and plays 0, 1. So here it is, having played 0, 1. I roll a 3. So let's follow the rules. Let's put it in the same column as his 6. Solver rolls a 3 and eliminates. So what did solver choose to do? Solver chose to eliminate. That was the highest thing on our hierarchy. Makes sense. Solver is crushing me already. What are you gonna do? We roll a 3 though, so that's pretty good. Let's eliminate our opponent's 3. Solver rolls a 4 and plays it in the same column. Now, it's already a little interesting that he plays it in the same column here, right? That means that he's giving up the opportunity to triple sixes here. That's interesting. That might immediately be something that I want to look into with the solver. And these sorts of situations do come up, and they're the situations that kind of make an exercise like this valuable. You look for those, you try to find the explanation. If you do, you learn something, hopefully. So I'm not going to play through the whole game. We'll just continue for a moment and eliminate our opponent's 6. Opponent rolls a 2, plays it in the same column. We roll a 4. And one thing that's kind of interesting is that we're being forced into playing a 4 on our same column as the 6. So our opponent, by playing on the same column as us, has kind of forced us to fill up a column, which can end up being advantageous later. So maybe that's the reason why he prefers to play in the same column. So we eliminate. He rolls a 6 and plays it. We roll a 2. We just keep playing in this same column. He rolls a 1. And now we roll a 3. And now we can see this at play, actually. So I suspect this might be the reason. We've now filled up this whole column. He can, if he ever rolls a 6, I mean, this 6 can never be eliminated, right? Unless he chooses to eliminate one of my dice. But this 6 is very secure if he wants it to be. And the same thing is true of whatever he puts here. He can leave this space free to double his 6 at some point. And that seems really valuable. And I can't double my 3, interestingly. So I'll put it off to the side, and we can keep going. But by playing against the solver, and I'd encourage you to clone the repo and do this yourself. You can find instructions in the README. You see these interesting situations come up. Solver does something different than you would expect, and the solver beats you most of the time. You'll certainly beat him. Sometimes it's a game of luck, but the solver has certainly beaten me multiple times, and it felt like he swindled me out of games several times. So just a couple other interesting scenarios here. One is this one, where we have 2 2s. We've doubled them already. Player 2 has wound up with this column. And this is basically the situation that we just saw in the game I just played against the solver, where if we roll a 5, 5 is strong. We want to play it opposite his column that's full, because then he can never eliminate our 5, and we really don't want him to, because 5s are strong. We want to put as many 5s and 6s on the board as possible. So we're going to try and load up 5s and 6s in this column that he can't eliminate. And this comes up pretty commonly, and now that I'm thinking about it, given that game I just played against the solver, I think this is the reason why solver likes to play on the same column. It incentivizes this sort of structure to show up, which then solver can take advantage of. The other insight I wanted to point out is endgame strategy. Now, typically in the endgame, it's going to be pretty clear what you want to do. Usually you can follow that hierarchy. Usually you can just follow common sense. You're trying to end, if you're winning, you're trying to end the game quickly. If you're losing, you're trying to keep the game alive. In general, elimination is going to be good, then tripling, then doubling, the same thing holds. But there are situations that you want to look out for where that's not going to be the case. And so here's one of those situations. So we're pretty close to the end of the game. Player 1 has 2 moves left and has just rolled a 2. Player 2 has 3 moves left. And interestingly, player 1, the optimal move for player 1 is to put this 2 not in 2, where he would be tripling 2s, but in 0, 1, which is where, yeah, he's doubling his 2s, but more importantly in this situation, I think, he's avoiding a very bad roll for his opponent. So if his opponent rolls a 2, his opponent now can eliminate 2 of his 2s. It's still bad. He can eliminate 2 of his 2s by putting it in either of these columns, but he can't eliminate 3 of player 1's 2s. He can't eliminate a whole row of 2s, which is a big difference because player 1's trying to end the game. Player 1 is slightly winning here, and wants to end the game as soon as possible, he needs these extra tempi. He can't afford to all of a sudden have the game reversed and have player 2 be threatening to end the game and fill up his board first. Now, if we put 4s or 5s, if we made the same situation with 4s or 5s, it starts to tip back the other way, because at a certain point, points are really valuable, especially to the heuristic. The heuristic is going to evaluate, 3 6s here very, very highly. My suspicion is that this solver underappreciates these situations where you're actually giving your opponent outs to win if you triple your 2s here. And so solver is figuring it out here on depth 6. When I bumped these up to higher values, solver wanted to go ahead and triple the 4, triple the 5. My guess is that on high enough values, even some of those might not be the right play. You really want to cash in on your win once you get close. If you're still 5, 6, 7 tempi from the end of the game, then I doubt that you want to do that. I think you want to prioritize score, because there are just too many ways for the game to end up going longer. You can't really guarantee that you can keep your position. But when you're 2 or 1 tempi away from the end, you can prefer to try to end the game quickly rather than sort of grabbing points. So an interesting thing to keep in mind. And this applies in other games also. Sometimes you just want to take the low variance outcome to end the game quickly, because it doesn't matter if you win by 100 or you win by 50. You just want the game to end. You're going to win regardless. And that's that. Those are the insights for Knucklebones. I really enjoyed writing up this solver, thinking through the strategy that I expected to see, and coming up with some interesting insights at the end of it. It's also pretty fun to play against the solver. The solver seems to be quite strong, and so I felt like I learned something just by playing against the solver, whereas the enemies in Knucklebones, they're not really playing very well for the most part. I guess I don't have the hardest ones unlocked, so maybe there's an optimal one somewhere in there. But for the most part, it sort of just seems like they play quasi-randomly. Not as much fun to play against them. Just to summarize the insights once again, in general, you want to kind of have this hierarchy in mind of you'd rather double than not. You'd rather triple than double. You'd rather eliminate than double or triple, maybe with some exceptions when you're tripling 5s or 6s, or there are some endgame considerations, but for the most part, you can go a long way by just preferring elimination to anything else that you can do in the game. Again, there's an exception here to tripling if you are winning. If you're up tempi and you're just trying to end the game quickly, you can diversify where you put your dice rather than doubling or tripling to end the game fast. Maybe the most interesting insight from this, and one that I didn't fully appreciate, I don't think, until I was recording this and played against the computer, you want to prefer playing your dice on columns where your opponent already has dice, especially in the early game. Obviously, if you're eliminating your opponent's dice, that's great. But even if you're not, you're forcing your opponent to fill up their column with dice if they want to eliminate yours, which is advantageous to you because then it gives you a hiding place for you to put your valuable dice. So once they've filled up a column with dice, they can no longer eliminate your dice on the other side of the board, and that gives you a place to stash your 5s, your 6s, your doubled dice. And that's the last little insight here. Hide your good dice behind your opponent's full columns to prevent elimination. So I hope this has been interesting for everybody. I found it really valuable to think through it. I think the thought process is more important and more valuable than the ability to win at Knucklebones. Sort of a minigame, unimportant, trivial thing, but this game is a really nice example that feels similar to games like backgammon or other games where you roll dice, you take chances, and you try to win. So I thought solving this was really interesting. If you want to see how the sausage is made, I stream at Coding Mental Models on Twitch. I streamed almost the whole development of this solver. You can see how I think through that process, how I come up with an approach, how I implement it, the problems I run into, the debugging sessions that don't go well. It's pretty fun and interesting, and I hope to see you there. Thanks.